Hey everyone, and welcome to The Explainer. Today, we're taking what looks like a standard, maybe even slightly dry physics paper, the kind packed with equations and rigid diagrams, and we're going to transform it into a complete visual journey into the world of optics. We're looking at spherical mirrors. We'll see how they manipulate light, create images, and even harness the raw power of the sun. So let's jump right in.
Okay, let's dive into this with a bit of a real-world mystery. Picture this. You're holding a mirror in your hand, directing the reflecting surface straight towards the blazing sun, and then angling that reflected light onto a simple sheet of paper. Could you actually start a fire? The physics paper we're exploring today challenges us with this exact scenario. And it turns out, the answer relies entirely on knowing how to manipulate light rays to a very specific, intense focal point. But to understand exactly how that works, we first need to understand the tools at our disposal.
So, let's start with phase 1, C, the basics of spherical mirrors.
Now, whether you're dealing with a concave mirror, one that curves inward, kind of like a cave, or a convex one that bulges outward, we really need a mental map before we start bouncing light around. Imagine a hollow glass sphere. The exact geometric center of that complete spherical surface, that is our center of curvature. Now draw a straight line cutting right through the middle of our mirror segment, joining the pole of the mirror directly to its aperture. That straight line is our principal axis. Basically, every calculation we're going to do maps directly onto this invisible geometric grid.
To see why this geometry matters, let's look at two practical examples pulled straight from our source material. We've got mirror X and mirror Y. Mirror X is a concave mirror, the exact kind used in a massive solar furnace. It captures sunlight and forms an image that is real, diminished, and focused at a singular, incredibly hot point. That is absolutely perfect for our paper burning experiment. Now contrast that with mirror Y. This is a convex mirror, like the ones you'd find on the side of a vehicle. It takes a wide field of traffic and forms an image that is virtual, diminished, and erect, allowing a driver to safely see exactly what's behind them. The shape of the mirror completely dictates its superpower.
Moving right along to our next section, understand visualizing light paths.
Now, what's really interesting about this slide is how these mirrors actually operate. They strictly obey the immutable laws of reflection. The angle of incidence always equals the angle of reflection. Take a look at the complex reflection diagram we're decoding here. See object AB on the left? To figure out where the mirror projects this object, we don't need to track every single photon. That'd be impossible. We just need to track two key rays originating from point A. Our source document actually asks us to complete this exact diagram, and doing so reveals the hidden mechanics of the mirror.
So let's walk through the exact procedure for completing this ray diagram. Honestly, it makes the visual math feel incredibly simple and logical. Step 1, trace ray 1 parallel to that principal axis we defined earlier. The golden rule here is any ray parallel to the axis always reflects straight through the mirror's focal point. Step 2, trace ray 2 as if it's heading straight for the center of curvature, point C. A ray aiming for the center reflects straight back along its own path. Where those two reflected rays intersect, boom! That is exactly where your image forms. It's just beautifully predictable.
And this predictable nature applies across all the different scenarios outlined in our physics paper. Let's fire through a few. If you have a parallel incident ray hitting a bulging convex mirror, it reflects outwards, but if you trace it backwards, it appears to come perfectly from the focus behind the mirror. Next scenario. If a ray passes through the principal focus of a concave mirror, it bounces off perfectly parallel to the axis. And finally, if a ray comes in obliquely, hitting exactly on the pole of a convex mirror, it reflects away obliquely, mirroring the exact angle. No matter how the light arrives, the surface processes it with perfect mathematical consistency.
But here's a critical question for when we actually start doing the math. How do we know if our measurements are supposed to be positive or negative? For that, our source text relies on the Cartesian sign convention. Think of it like laying a standard XY math graph right over our mirror, with the mirror's pole sitting dead center at the 0, 0 origin. Anything in front of the mirror, where the light is actually coming from, is usually negative. Anything behind the mirror is positive. Heights above the axis are positive, below are negative. It's just a really simple set of grid rules that keeps all our optics calculations perfectly organized.
Let's move to our final phase and see how this all builds. Calculate, mirror math, and magnification.
All right, we've traced the lines, and now we're going to predict these reflections using pure numbers. In our source text, one of the questions gives a specific magnification value of -3. Let's isolate that for a second. What does it actually mean? Well, in optics, every symbol tells a story. The negative sign tells us the image is real and inverted, meaning it's physically projected in front of the mirror, but it's upside down. The number 3, that tells us the magnitude. The image is exactly 3 times larger than the actual object. 2 tiny characters giving us a complete physical description of the reflection.
And you'll be glad to know the math governing the mirror's curve is just as elegant. One of the problems asks for the focal length of a convex mirror that has a radius of curvature of 32 centimeters. The relationship here is brilliantly simple, proportional math. The focal length is always, without fail, exactly half of the radius of curvature. So, half of 32 means our mirror has a focal length of 16 centimeters. That one simple division unlocks the mirror's entire capacity to bend light.
And this brilliantly illustrates how just varying those distances changes everything. What we have here is a data set from the source comparing 3 different concave mirrors, A, B, and C. We know their focal lengths, and we know exactly how far away an object is placed from them. By just looking at these numbers and knowing the rules we just discussed, we can predict exactly what the resulting image will look like without ever having to draw a single ray.
Let's actually decode that data together. For mirror A, the focal length is 20, making its center of curvature 40. But the object is at 45, which is beyond the center. The laws of optics tell us this is going to form a diminished, smaller image. Now look at mirror B. The focal length is 15, meaning the center is 30, and the object is placed exactly at 30. When an object sits right in the center of curvature, the image is the exact same size, real, and inverted. And mirror C? This one's fun. The focal length is 30, but the object is up close at 20. It slipped the object right between the pole and the focus. This creates a magnified, virtual, and direct image, exactly like looking into a magnifying shaving or makeup mirror. The numbers reveal the hidden patterns perfectly.
Let's tie it all perfectly together with one final practical calculation from our source. We have a concave mirror. The focal length is 12 centimeters. Since it's concave, our Cartesian rules tell us that's a negative 12. The object is placed at 18 centimeters in front, so that's a negative 18. Using our trusty mirror formula, 1 over the focal length equals 1 over the image distance plus 1 over the object distance, we just plug in our negative 12 and negative 18, run the fractions, and you find the image position is exactly negative 36 centimeters. A real projected reflection calculated with absolute precision.
We've gone from a theoretical piece of paper to literally burning pages with the sun, from tracing simple lines to calculating the exact mathematical coordinates of light itself. You now have the fundamental map of how spherical mirrors work. So, I leave you with this. The next time you look at the curved security mirror in a convenience store, or the passenger side mirror on your car, don't just look at the reflection. Look at the math. Look at the invisible geometry shaping the light. Look around. What hidden magic of reflection will you calculate next? Thanks so much for joining me on this explainer, and keep exploring.